Hey everyone, just decided to make my own video this week to go along with section 11.7 in the book, which is the counting principle and permutations. We'll also be talking about 11.8 as well as 11.9 in the book. So 11.8 is going to be combinations, and then 11.9 will be solving probability problems by using combinations. Basically what we're going to do on this one is there's only certain things in each section that I want to cover, so we won't be looking at the entire section. So if you'll just get your book out, go ahead and turn to page 689, section 11.7. I'll just kind of guide you through in this video exactly what I want you to look at, exactly what examples I want you to look at, and then what problems to do for homework. I'll also jot those down on Canvas as well for you in one place. So here we go. So in general, the counting principle says that if we have two experiments, and we can perform the first experiment in m ways, and we can perform the second experiment in n ways, then the two experiments can be performed m times n ways. So really simple example of this would be if you had in your closet, you had 4 different colors of shirt, so 4 shirts we'll say, and you also had 3 different styles of pants. And if I wanted to know how many different ways you could design an outfit using those 4 shirts and 3 pants, and of course we assume that all those things go well together and we don't have any clashing colors or anything like that, so every combination is a possibility, then the counting principle says that we can create 4 times 3 or 12 unique outfits. So that's a very simple application of the counting principle. Example 1 in the book on page 689 is talking about using the counting principle to determine how many different unique passwords that we can create to gain access to a computer account. Now, in this example, the requirements for that password are very specific. Now, we know that when we make passwords for, like our Facebook accounts and things like that, that those passwords can be a lot more complex than what's going on here. But this is just sort of a simpler example so that we can talk about it with smaller numbers and make it a little bit more easy to kind of comprehend and understand. So basically what's happening here, it says a password used to gain access to a computer is to consist of 2 lowercase letters followed by 4 digits. So if you've got 2 lowercase letters first, then in this very first slot here we can have A through Z. That's 26 options. Second slot we can have A through Z. That's 26 more options. And then we can have 0 through 9, 0 through 9, 0 through 9, and 0 through 9, which is 10, 10, 10, and 10 more options. So and the book kind of shows you that there in the solution to this problem. Part A says to tell how many different passwords are possible if repetition of letters and digits is permitted. So that means theoretically I could have the password AA0000, and that would be okay. So I can repeat the letters, I can repeat the numbers, and that's alright. So for that one, then we really just need to do 26 times 26 times 10 times 10 times 10 times 10. So the counting principle applies there, because this would be 1, 2, 3, 4, 5, 6 different experiments. So we chain together that multiplication. So it would be 26, 26, 10, 10, 10, and 10. And as you'll see, that's a giant number. You'll get 6,760,000 unique combinations for that password. Part B goes on to say that the repetitions of letters and digits is not permitted. So for that one, instead of having 26, 26, and then 4 10s, you'd have to have 26 for the first letter, and then 25 for the second one. So if you used A for the first one, you couldn't use A for the second one. And then same for the numbers. It would be 10, 9, 8, and 7 combinations. So multiply all that together, you end up with a smaller number, but still pretty large. That'd be 3,276,000 combinations. And then for example C, it says the first letter has to be a vowel A, E, I, O, or U, and the first digit cannot be a 0, and repetition of letters and digits is not permitted. So for the first slot, you have to have a vowel, so there's only 5 choices there. The second slot can be any letter, but you can't repeat digits. So if you used A in the first one, you can't use A here, so there'd only be 25 other letters for that one. It says the first one can't be a 0, so it's got to be 1 through 9. That's 9 choices. If you used, I don't know, 8 for that first choice, and you'd only have 9 more choices for this one because we can't repeat, and then 8, and then 7. Okay? So first thing I'm going to do is create a password under these guidelines. The first letter has to be a vowel, so I'm going to use the letter O. The second letter can be any other letter in the alphabet. I'm going to use F. This number can't be a 0, so I'm going to use the number 2. The next one can be any digit, but it can't be 2 because I've already used 2. So that gives me 9 more choices. I'm going to pick 8. The next one can't be 2 or 8, but it can be any of the other 8 digits. I'm going to pick 0. The next one can't be 2, 8, or 0, but it can be any of the other 7 digits. So I'm going to put 1. So there's my password, OF2801. That would fall under those category, under the guidelines rather. So multiply that together, you get 567,000. 567. And so that's how that example works. Okay, so for the first part of your homework, flip over to page 696 and give problem number 30, parts A and B. So it's a license plate problem. You've got 2 parts there, one with repetition allowed and one with repetition not allowed. So read through problem 30, try parts A and B. So the next concept in this section, on page 691, we talk about permutations, and the first thing we do is give you the definition of that. So permutation is any ordered arrangement of a given set of objects. I always say with permutations, just remember that order matters. So for example, the first example they give you is the Three Stooges, Larry, Shemp, and Moe, and it says that Larry, Shemp, Moe, and Shemp, Moe, Larry represent 2 different ordered arrangements or 2 different permutations of the same 3 names. When you see names or people typically in permutations, you want to think about things like first place, second place, and third place. So for example, if you had 3 people that were in a competition for an award, and let's say that Sally won first place and Timmy won second place and Sheena won third place. Well, that's one permutation, but you could also have another permutation where Sheena won first place. So order matters there. Like the first place is different than second and third place. The winner is going to get something different or a better prize or whatever the case may be. So order does matter in a permutation, and that's what they're all about. So there's a formula for finding permutations. So if you want to select R objects from a group of N objects, then you use this formula. NPR equals N factorial over N minus R factorial. So the first thing you need to know about this formula is this notation is just simply that. It's just notation. So that's like when we say the probability of an event, we use P and then parentheses event. That just means the probability of some event happening. NPR is just notation for, like for example, selecting 2 objects from a group of 5 would be 5P2. And so if I wanted to put that into the formula, I would just do 5 factorial over 5 minus 2 factorial, or 5 factorial over 3 factorial. Now, the second thing you need to know is, what does this factorial thing mean? Your book shows you an example of that. 5 factorial basically means 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And then your book shows you this little trick where any duplicated factors on the top and bottom you can cancel out. So really what you're doing is 5 times 4, which is 20. So if I have a group of 5 things, let's say for example I have 5 contestants in a raffle, and I'm going to draw 2 names out. I'm going to draw a grand prize winner and I'm going to draw a second place winner. Then according to this math, there are 20 ways in which I can do that out of that group of 5 people. Okay, so that's what a permutation is, and that's a simple example. Now, as far as your homework problems go and your test questions next week that have to do with permutations, you're more than welcome to use that formula, and you're more than welcome to do them by hand. However, there is an easier way. So your calculator will do those as well. So if you find on your calculator the permutations button, and for those of you with like a TI-30, one of the smaller non-graphing calculators, there's actually a probability button. It's on the second row of buttons that says PRB. So in order to do 5P2 in that, you'd have to type in 5 and then hit that probability button and hit NPR and then hit 2 and hit enter, and you should come up with 20. If you're using an 83 or an 84, one of the bigger graphing calculators, it's located under math, and then it's in a probability menu. There's an NPR and an NCR. You use it much the same way. You type in 5, you hit math, you go over to probability down to NPR and hit enter, and then you push 2 and then hit enter again, and it should give you 20. If you have any issues with that, or if you have a different calculator, you can probably YouTube a quick tutorial. If you just type permutation and then type in the name of your calculator, I would be willing to bet you could find a tutorial. And if not, you can let me know and I can maybe help you find one, or I can show you how. If you want to come by the office, I can show you how to do it. So you're certainly going to be able to use your calculator on the test. So if you find a way on your calculator to do these permutations and combinations, because there's a combination formula too, which we'll talk about in a bit, then you're more than welcome to use your calculator. You don't have to do these calculations by hand like this. Okay? So that's all I have to say about that. Alright, homework on permutations. You're going to look at number 41 and 42 on page 697. Okay? Okay, so that's all we're going to look at for 11.7. Just make sure you can do the counting principle problems and the permutation problems, and you should be fine for next week. Moving on to section 11.8 with combinations. This is the point, or this is when we talk about distinct groups of objects that it doesn't matter what order they're in. Okay, so order doesn't matter. And actually, I'll go ahead and just do that. I'll just talk about that right now. So when we talk about combinations, remember, order doesn't matter. Okay, and just as a kind of a side note, something interesting to think about, if I tell you to think about a combination lock, you think about that lock that has a dial and there's some numbers. You're not allowed to make fun of my art. That's not cool. I see you making fun of my art. And of course, you turn the dial in, usually it's to the right first, and then to the left, and then to the right, or to the left first, and to the right, and to the left, and you go to 3 different numbers. Those are actually permutations because the order matters there. If your combination's 5, 2, 1, you can't put in 1, 5, 2 and expect it to work, right? That would be a combination. It's actually a permutation lock, but I think that the marketing department probably didn't like that wording. They thought permutation was a complicated word, so they just called them combination locks. That last part is something I just made up, but it sounds good, right? So, yeah, those are permutations, not combinations. Alright, so moving along, the very first example just talks about permutation or combination. So this is just kind of an exercise that we can talk through. There won't be a lot of writing here. So the first one says to determine whether the situation represents a permutation or a combination problem. A group of 5 friends, Arlene, Inez, Judy, Dan, and Eunice, are forming a club. The group will elect a president and a treasurer. In how many different ways can the president and the treasurer be selected? So the first question I have for you is, if Arlene and Eunice are selected, and let's say that Arlene is the president and Eunice is the treasurer, would it be different if I switch those 2 names and I put Eunice over here, and I put Arlene over there. And hopefully you're thinking, yes, it would be different, because in the first arrangement, Arlene would be the president, and then the second arrangement, Eunice would be the president. So since the order matters there, this is a permutation. And we would use our NPR formula. Okay? Part B says, of the 5 individuals named, 2 will be attending a meeting together. In how many different ways can they do so? So, alright, let's go back to our original example here. Now we don't have a president and a treasurer anymore. Now we just have an attendee and another attendee. Now, does it matter if I put Arlene as the first attendee and Eunice as the second attendee, or Eunice as the first one and Arlene as the second one? No, it doesn't matter anymore. So this just went from being a permutation in part A to being a combination in part B. Doesn't matter which order we select them in. One's not more important than the other one. Alright, so quickly, here's the formula for combination. It's very similar to the permutation formula. We just add one more little extra piece here at the end. That's really the only difference between the two. The factorials are the same. They're calculated the same. They're kind of thought about the same. So let's just use our example from before. So let's say we want to take those 5 people, and we want to see how many combinations of 2 of them we can have. So if I'm using the formula by hand, that's going to give me 5 factorial over 5 minus 2, or 3 factorial, and then r factorial, so that's 2 factorial. So if I write all that out, it's 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. Okay, so I can do a little canceling. Do this in a couple different colors so you can see what I'm doing. 3, 2, 1 times divided by 3, 2, 1. That's going to cancel out. And then I can actually also do this. I've got a 4 there and a 2 there. I can't get rid of those, but I can divide 2 into 4. 2 goes into 4 2 times, and it goes into 2 1 time. So now I just have a bunch of 1s on the bottom, right? Everything's canceled out but 1 times 1. And on the top, I've got 5 times 2. That's 10 over 1, or just 10. So there's 10 different ways I can select those 2 people out of a group of 5. But again, use your calculator. Learn the process in the calculator and be ready to do that on the test on Tuesday. You're welcome to try these by hand. You're welcome to look at them in the book. The book does them all the long way. So check them out in the book, but don't feel obligated to use the book, okay? Or excuse me, to use the formula. You can use your calculator. All right, so let's try an example. All right, so I kind of set this up a little bit so that we can talk about it. It says at the Oriental Cafe Chinese restaurant, dinner consists of selecting 3 items from column A, 4 items from column B, and 3 items from column C from the menu. If columns A, B, and C have 5, 7, and 6 items respectively, so 5 in column A, 7 in column B, 6 in column C, how many different dinner combinations are possible? So the first thing we need to do is see how many choices or how many combinations we can have in each column individually. So in column A, oh, and by the way, order doesn't matter here, right? Because if I pick the General's chicken first, and then the sesame chicken, and then the mushu pork, or if I pick the mushu pork and then the sesame chicken and then the General's chicken, I'm still getting those 3 items. It doesn't matter which order I put them in. So this is a combination 5, choose 3. Column B is 7, choose 4. Column C is 6, choose 3. So the first thing I need to do is just do those combinations. Again, you can use your calculator for these. I've got 10 combinations in the first column. I've got a whopping 35 combinations in the second one. And I've got 20 combinations in the third one. If I want to know how many combinations in all that I have, then I'm going to use the counting principle. Okay, I've got 10 choices for the first blank, I've got 35 choices for the second one, and I've got 20 choices for the third one. So 10 times 35 times 20, or 7,000, is the number of choices I have in all. This is just like, once you get past the combinations part that we just talked about, this is just like the license plate problem from earlier, okay, or the password problem. I've got 3 blanks, and I've got 10 choices for the first one, 35 choices for the second one, and 20 choices for the third one, okay? 7,000 choices in all. All right, add number 40 from page 703 to your homework. And that's it for 11.8. So 11.9 is called solving probability problems by using combinations. So this is basically putting together the things that we've been talking about with probability and what we just discussed in permutations and combinations, specifically combinations in this chapter, or in this section rather. So these, in my opinion, is where the combination problems really come to light. They really start to make sense of why we care about how many different combinations. It's so that we can calculate probabilities. Okay, so the first thing that the book talks about in 11.9 is using the AND formula. So they give you this example on page 705 of the probability of getting 2 picture cards. I typically call those face cards. So picture cards, face cards, would be equal to the probability of getting a picture card first times the probability of getting a picture card second. And it says without replacement. So your first one is going to be 12 out of 52. There's, ace, king, queen, jack, and then there's 4 suits. So, no, sorry. There's king, queen, jack, and there's 4 suits. So that's 12 different possibilities. So 12 out of 52 for the first one, 11 out of 51 for the second one, which becomes 132 over 2652, or 11 over 221. So they're reminding us there that if we want an AND probability, then we multiply our 2 probabilities together. Okay? So they're just showing us another way of looking at that. So if you come on down all the way to where it says, thus the probability of selecting 2 picture cards is equal to a combination of 12 pick 2 over a combination of 52 pick 2. Okay? And we get the same numbers. We get the 11 over 221. Okay? So it says, to give you more exposure to counting techniques, combinations, we'll work the problems in this section using combinations. Okay? So let's take a look at example 1. Alright, so basically the problem for example 1 is talking about a club that has 4 men and 5 women in it. So 4 men, 5 women, and we'll need, in just a second, that's a total number of 9 members. So I'm just going to jot that down so it'll be right there in front of us. And I want to know the probability that if I pick a 3-member committee, I want to know the probability that committee will consist of all women. Okay? So the probability of the committee consisting of all women, or 3 women, would be equal to the number of possible outcomes with 3 women in them, or, remember there's 5 women, so 5C3. Okay, that would give me all the combinations of just the women. And then, since there's a total of 9 people, the total number of possible 3-member committees is 9 choose 3. Okay, so the top of that's going to be all the combinations that are just women, 5 choose 3. The bottom's going to be all the combinations selecting from all 9 members, which would be 9 choose 3. So 5 choose 3 would be 10. 9 choose 3 would be 84. That reduces to 5 over 42. And so the probability of randomly selecting a committee with 3 women is 5 out of 42, which is about 12%. Okay? Doesn't really tell us we have to make it percentages, but I think it's easier to think about. So we've got about a 12% chance. If I've got 9 members, choose 3 at random, that's going to be about a 12% chance of it all being women. Okay? So let's go ahead and take a look at another one. All right. One of the easiest applications of probability to sort of see in the real world is using cards and poker hands. So don't worry, you don't have to know about the game of poker to do this. All you have to know to do this problem is that a flush in poker is choosing 5 cards of the same suit. So having 5 hearts, 5 diamonds, 5 clubs, or 5 spades. It doesn't matter what cards they are, just so they're all the same suit. Then you get what's called a flush, which is actually a pretty rare and pretty powerful hand in poker. So basically, this question's asking, if you're dealt a 5-card hand, determine the probability that you'll be dealt a heart flush. Okay, so since there are 13 hearts in a deck of cards, then the total number of possible 5-card heart flush hands, okay, would be 13 choose 5. So there's 13 hearts, and I want to pick 5 of them, and I want them all to be hearts. So it's 13C5. Doesn't matter what order I'm dealt them in, okay? So, for example, if I had the 2 of hearts, the 5 of hearts, the 7 of hearts, the 9 of hearts, and the 10 of hearts, it wouldn't matter if I got dealt the 2 first or the 10 first. Just so I was dealt all 5 of those, that would qualify as one of the hands that would win, okay? Or one of the hands that would be a heart flush. The bottom of this is going to be the total number of possible 5-card hands. So there are 52 cards in the deck, and I want to choose 5 of them. So that would be all the possibilities for all the hands I could get out of 5 cards. Okay. So in other words, the top number is going to tell me how many heart flush hands there are possible. That's 1,287. So there's 1,287 combinations of cards that'll produce heart flushes. And then the bottom is going to give me 2,598,960. That's how many different combinations of 5 cards you can get out of a deck. That's crazy, isn't it? So that's going to reduce down, but it's going to end up being the decimal 0.000495, which is less than 0.05%. Okay, so it's very, very slim. The chances of getting this hand dealt to you are very, very small. Okay, and that's why it's so powerful of a hand. It's very, very hard to get it. All right, ladies and gentlemen, the last homework assignment for this chapter is going to be page 709, number 31, 32, and 33. Let's go ahead and throw 34 in there too, since it's about the same problem. So all 4 of those questions are about that breakfast cereal example there at the top of page 709. So go ahead and try 31 through 34, and that'll be the end of your homework assignment. All right, roll the credits. That's all I've got for you today. I know that was a lot, but the good thing is if you followed along with this video and you've done the homework as you go, then you should have done your entire homework assignment, and you should have a pretty good review, since we won't get to actually spend some class time on this stuff, of 11.7, 11.8, and 11.9. Now, we didn't cover everything in all 3 of those sections, so the things that I didn't talk about, you don't have to be responsible for the test, okay? So just focus on the things that I talked about and the examples that I gave you, all right? I'll see you next week.